that's moving looks like what's not moving. And the detectability and the sharp edges all come back. So innovations in nanotechnology are also driven by innovation in instrumentation and reconstruction and imaging. And there are many more points about this in terms of mapping out the B1 and getting uniform fields and so forth. But just take my word for it. Now, drug delivery is a key element of image-guided drug delivery. And what we do is we target through a receptor, and drug, which is located in the membrane, as I mentioned, is delivered to the target membrane without the particle having to go in. And you can see the red, for instance, in this rhodamine particle circulating all through the membranes of the melanoma cell here. It's really accomplished through a hemifusion process. So the driving energy, even though I write passive, is actually the curvature of the particle binding to the membrane, which drives the surfactants, which are on the surface, to mix into the cell membrane down that gradient. But that gets it to the outer leaflet of the membrane. It doesn't bring it to the inner leaflet. And research in our lab, published here by Sam Wickline in particular with his students, showed that this is actually a lipid raft-associated phenomenon, and it's ATP dependent. So it requires ATP to go from here, from here to in here. And then once in the inner leaflet, you'll see in a moment it goes everywhere through all the membranes of the cell. Well, one of the reasons we're so interested in image-guided drug delivery is basically to take drugs like fumagillin, deliver it to tumors to provide anti-angiogenesis activity at much lower concentrations than, for instance, the water-soluble